Yeah, so we talked last time, and there's no video for that one, about the finite field extensions, right, as well as the cyclotomic field extensions, and so that was sections, 14.4 and 14.5 in Dummett and Foote, and so I'll try to remember to, in the playlist, I'll put a video from a past year for the people who aren't here. I know you were here to see it, but anyway, so that brings us to section 14.6. Which is one of my favorite. It's the Galois groups. Of polynomials. It seems like, well, isn't that what we've been doing? Well, yeah, it is, isn't it? So what does this mean? All right, well, let's just follow along here and just reiterate what's going on. So if K is a Galois extension of F, then K is the splitting field of some separable polynomial over F, right? So if K over F, if this is Galois, then K is splits f of x, some f of x, with coefficients in x, right? In f, rather. And more than that, we know that if we look at sigma, an element of the, the Galois group of K over F, what was that defined to be? It was the, K fixing, F, here F fixing automorphisms of K, right? And what did those do? What did those do? So also, something else we knew is that K contains all roots of f of x, right? And we're also assuming that f of x is separable, right? Ooh. Sometimes if you pinch chalk like that, it'll hurt your finger. Anyway, K contains all the roots of f of x, right? And so if you want to call those like alpha 1, alpha 2, say alpha n, right? And what happens if you, operate by that sigma? What do you get? You get, sigma of alpha 1, sigma of alpha 2, right? Sigma of alpha n, but what can you say about this? Well, these are the same roots, right? So remember we had the theorem that the f-fixing automorphism of K, it maps a solution of f of alpha equal to 0 to a solution of f of, it gives us f of sigma alpha equal to 0, right? So, in fact, this is the same, if this list is equal to, if this is the list of the roots, right, then this over here is still that same set, right? What I'm trying to say is that sigma permutes the roots. Permutes the roots of polynomial which this field splits, right? And as such, there is a natural identification of an f-fixing automorphism of K with a corresponding permutation of the numbers 1 through n. So, like, for example, if you had, suppose you had 3 roots, right? Alpha 1, alpha 2, alpha 3. And they map to, alpha 2, alpha 3, alpha 1. In other words, this is sigma of alpha 1, sigma of alpha 2, sigma of alpha 3, right? Yeah, so this is 1 goes to 2, right? I mean, so in the big notation, you'd have 1, 2, 3, 1 goes to 2, 2 goes to 3, 3 goes to 1, right? That's another notation for, well, I wouldn't say, maybe I should say sigma tilde. So that sigma tilde is the corresponding permutation in S3 corresponding to my sigma. What's the cycle notation for this? Let's see here. I can start with 3. I'll start with 1. Where's 1 go?
1 goes to
2. Okay. Where's 2 go? 3. Where's 3 go? 3 goes to 1. Yeah. Okay. So yeah. So this is the 3 cycle. Sigma tilde is the 3 cycle, right? And of course, which is an element of what we typically call S3 in this case, right? Okay, so the point is, if you enumerate the roots of the polynomial which you split, right, is 1 through n, then since any automorphism permutes the roots, there's a natural permutation in Sn which corresponds to the permutation alpha. And I've called it sigma tilde. This is the one that, this, for example. Now, so what he says is that what we have then is that the Galois group of K over F has a natural inclusion into Sn. And by that he means that there's a homomorphic image of the Galois group sitting inside Sn. We can think of any Galois group as is isomorphic to a particular subgroup of Sn. All right? Now, this is actually not surprising because there's a larger discussion in group theory that any finite group can be viewed as a up-isomorphism subgroup of the symmetric group.
Oh, is that because like everything in the group comes in the group again, so technically you're just permuting things?
Right. If you just label the group elements and then exactly every multiplication by any group element, it shifts the other group elements around. So you can look at that as a permutation. All right, so he points out that since the splitting field is the same order as the Galois group by the fundamental theorem, this explains from the group theoretic side why the splitting field of a polynomial of degree n is at most degree n factorial over f. So, see, if this is a subgroup, of that, the order, remember, of the permutation group is n factorial. So you can't have a subgroup which is larger than the group. So the largest the order of the Galois group, the upper bound on the order of the Galois group of K over F is the degree of f of x that is split at factorial. So the degree of Galois, the Galois group of f of x is less than or equal to the degree of f of x factorial, right? And then you're like, well, okay, that's great, but what about f of x which are not separable, He says, in general, f of x factors into irreducibles, f1 of x through fk sub x, and let's see here. Is he assuming f? I think he's still assuming f of x separable. Oh, okay. So this is not wrong, but we can say a little bit more. Moreover, for f of x separable, we have f of x equal to f1 of x f2 of x, fk of x, all irreducible over f, right? Remember that we can take any polynomial and factor it into a product of irreducibles. And we know that those irreducibles are not repeated. These are distinct irreducibles because we're assuming separable, right? And so what happens then? What more can we say? He says, since the Galway group permutes the roots of irreducible factors amongst themselves, that's the other thing, is like, you know, if we have, so if sigma, I don't want to introduce a notation for it, but I guess I need to. Suppose this one has roots alpha 1, 1 through alpha 1, n1, right? Roots for f1 of x, right? This guy, alpha k1, alpha k nk, roots for f k of x. And I'm just having a mental block all of a sudden. Why is it that, I'll ask the question, maybe you can answer it. Why does sigma, a element of the f-fixing automorphisms of k, right, send alpha, let's say 1i to sigma to alpha 1 comma j for some j. And so what I'm saying is that it permutes the roots of f1 of x.
Yeah, I got the question. So why does it do that?
Yeah, why can't it move one of the roots from one of the irreducible factors to another? Why does they have to be?
Why do they have to be separable?
I mean, why do the roots of f1 of x have to map to the roots of f1 of x under the automorphism? Why can't they map to the roots of one of the f2 of x's roots, you know? So we're given f of, say, alpha 1i 1 equals to 0, right?
Alpha 1. Well, this is how I interpret his question.
Let me just one second. Why is f sub, let's say, L, any choice, J, whatever, of alpha 1 comma I equal to 0 forbidden? See, now that I write this out, I know the reason.
Why is it forbidden? Like, why can it never happen ever?
Yeah, why is it for these distinct irreducibles, right? These are irreducible factors of f of x.
Yes.
The claim is that if you have a root of one irreducible factor, it cannot be a root of another distinct irreducible.
Why would alpha map to beta, though? Like, if you have an alpha for f1 and beta for f2, like, how would you send alpha through sigma to give beta?
Well, alpha and beta are both roots of f of x.
But if you have two irreducible...
I mean, we do know that the roots of f of x map to the roots of f of x, but how do we know that the roots of f1 of x map to the roots of f1 of x, and the roots of f2 of x map to the roots of f2 of x, and so forth and so on? through the arbitrary f-fixing automorphism, okay, in the Galois group of here, f of x. What would it mean if these two were both 0, right?
Well, you have a repeated root.
Yeah, well, in some sense, right? We'd have, that would mean that we had,
You're missing a I mean, you'd be missing a polynomial, wouldn't it?
yeah, I mean, that would mean that we have x, so that would mean in the splitting field,
Yeah.
right, in K. Let me write it out. This says that x minus alpha 1I divides f1 of x, right?
Yeah.
And this says that x minus alpha 1I divides fl of x,
Yeah.
which means that it's not separable, because when you go back to the original equation, you have this factor of x minus alpha 1I in both factors. So when you multiply it out in the splitting field, you have x minus alpha 1I squared, which means it's not separable.
Yeah.
So the irreducible factors cannot share roots, because if they did, in the splitting field, that means that they share factors, and if they share factors, when the factors combine, we do not have separability. So it's that.
So you basically, like, if these, okay, yeah, I get what you're saying.
So what that means then is that actually what's going on. So, okay, now we have that.
Yeah,
I mean-
because essentially when you square it out, like, you get a linear combination.
Square it out.
Like, you know, like x minus, like f of x equal to x minus 1 is not separable.
Yeah, I mean,
So that's all I'm saying, is that, like, when you get that squared.
yeah, it's awful, but in the splitting field,
Yeah.
this is f of x is equal to, the product of, let's say, I equals 1 to n1 of x minus alpha 1I. I'll put a 1 here, just to be really annoying. And then you've got the product I sub 2 equals 1 to n2 of x minus alpha 2 I2. Ugh. And then you've got the product of ik equals 1 to nk, pun intended. I won't take it back. K comma ik, ich. So this is what's happening in K of x, right?
Yeah. K being a splitting field, right?
Right, because that's what it means for one of the characterizations of K being Galois over F is that K is a splitting field for some f of x, and this is the f of x we're talking about. So, yeah, again, if any of these factors correspond, right, we're up a creek, because then we don't have separable. Now, on the flip side of things, what's happening when you hit sigma? Then what's going on? How is sigma behaving? Sigma, like if we take a
When you have a non-separable polynomial, when you have a separable, like.
separable, we have a separable polynomial. We hit it with the f-fixing automorphism of K. What can we say about these buckets of roots? Like the sigma is just taking these. And
Does it take a bucket of roots to a bucket of roots?
takes the same bucket. Like bucket 1 goes to bucket 1.
Oh.
And so what we're really saying is that it's really like what? Sigma is corresponding to like sigma 1, sigma 2, sigma k, right? Where this one is a permutation on, well, sigma tilde, let's say. This is a permutation on, the symmetric group with n1 elements. This is a permutation on the symmetric group with n2 elements. This is a permutation on the symmetric group with nk elements. That's the structure of the corresponding, the permutation in Sn correspondingly. We can look at it as, in fact, a tuple of permutations where it's permuting these Sn1, Sn2, where those, of course, are the degrees of the irreducible factors. And so, long story short, this suggests that the Galois group, k over n over f in this case, it's actually something that's like a subgroup of Sn1 cross Sn2 cross Snk. It's you can actually look at it as being a subgroup of the Cartesian the direct product of symmetric groups of the orders of the irreducible factors. And that's the structure we see here. Now, if there's just one irreducible factor, there's just one Sn, you know. And most of the examples we'll ever look at will just have one Sn, but all right. So let's see here. In fact, he doesn't say this. He goes so far as to say less than or equal to. He says it's a subgroup of that. But of course, when he writes that, he's really exploiting an isomorphism, right?
Yeah.
Because unless you literally think of these as automorphisms on the set of roots, it's not accurate to say that's a subgroup. There's a subgroup of this which corresponds to the f-fixing automorphisms of K. All right. Anyway, so he says if f of x is irreducible, then any two roots of f of x, given any two roots of f of x, there's an automorphism in the Galois in the Galois group which maps the first root to the second. And he says such group is said to be transitive on the roots. That means you can get from any given root to any other root by applying some element of g. He says the fact that the Galois group must be transitive on the blocks of roots, namely the roots of the irreducible factors, can often be helpful in reducing the number of possibilities for the structure of G. And now he gives some examples to try to illustrate that, I guess. So the Galois group is transitive on the roots. All right, if you have two roots for your polynomial which is split, you can find a automorphism which maps that one root to the other. So that's we've done a lot of the other direction. We've done a lot of here's a root, here's an automorphism. Sigma of alpha is another root. This is saying something a little bit different. This is saying if you have two roots of an irreducible polynomial, then there is a something in the Galois group which will map that one root to the other root. So, all right, so let's look at the examples. I guess I'll hold off on this just yet. It's kind of I have to commit to like a moment of silence. If I use that at the moment, yeah. All right, so I think we've seen these examples before, but one, if you look at the biquadratic extension, this guy, right, splits. It splits x squared minus 2 times x squared minus 3 over the rationals, right? And he says label the roots. Alpha 1 square root of 2, alpha 2 minus the square root of 2, alpha 3 square root of 3, alpha 4 minus the square root of 3. All right? And he says so what is the Galois group? If I call this thing f of x, yeah. This is the Galois group of f of x is, 1 sigma tau and sigma tau, right? So let's try to understand that. Let's try to figure out what this looks like in cycle notation, right? So here, sigma of square root of 2 was minus the square root of 2, right? And tau of the square root of 3 was minus the square root of 3, right? So let me just be a little bit more explicit here. So what we have is sigma of alpha 2 equals, alpha 1 rather, equals alpha 2, and sigma of alpha 3 is alpha 3, and sigma of alpha 4 is equal to alpha 4. Remember, sigma fixes the third and the fourth roots here, and it permutes the first two. So this means that sigma in cycle notation is the 1-2 cycle. Because what does it do to 3 and 4? Yeah, preserves them, right? Now tau, likewise, right? Tau fixes, tau is the 3-4 cycle, since tau of alpha 3 equals to alpha 4, and tau of alpha 1 is alpha 1, tau of alpha 2 is alpha 2, right? So, and of course tau of alpha 4 is alpha 3 as well. I guess that kind of matters, doesn't it? So we have sigma is the 1-2 cycle, tau is the 3-4 cycle, and so in fact, the Galois group here of this f of x is equal to 1, 2, 3, 4, and then 1, 2, 3, 4. Right, and that's a subgroup of S4. So in fact, this is the Klein 4 subgroup, right? Because it's got 3 subgroups of order 2. His example 2 is, the splitting field of f of x equals to x cubed minus 2, I believe. Right. So, that you remember this is what? This is x minus the cube root of 2, x minus rho cube root of 2, x minus rho squared cube root of 2, right? And so if this is my alpha 1, this is my alpha 2, and this is my alpha 3, let's see, I'll try to use his notation. So in this case, he uses sigma as the one which, it says sigma is 1, 2, 3, is the 1, 2, 3 cycle, and tau is the, let's see here, what's tau? The 2, 3 cycle. What's that mean? That means, sigma of the cube root of 2 is rho cube root of 2, right? And sigma of rho cube root of 2 is rho squared cube root of 2. And sigma of rho squared cube root of 2 is cube root of 2. So that's one of the automorphisms of the splitting field here. And that corresponds to the 1, 2, 3 cycle. Tau, on the other hand, is what? What is tau?
Tau takes cube root of 2 to the cube root of 2.
Right, so tau goes like this, right? What is tau? What is the splitting field? This, remember, is, we can look at it as Q adjoin what? We worked it out before, like the cube root of 2, right?
Oh, it's like, it's just I root 3 over 2.
Right. Well,
Yeah, because you can get, it might be root 3.
I root 3, was that it?
Yeah, it might be root 3 over 2.
Yeah, he doesn't have those details here at the moment, but I think you might be right. I root 3. I think you're right. I root 3 is what I got to put there. But the point is that this is a subset of the complex. It's a complex field.
Yeah.
It's a subset of the complex numbers, right? What is tau? How do you get from this root to that root?
Oh, it's a conjugate.
Right. Tau is just complex conjugation here. So sometimes one of the Galois automorphisms will be complex conjugation. Not always, but like this one, there's no complex conjugation in this one, right? The splitting field's a real field, and the conjugates, the Q conjugates here, they're all, moving roots to minus roots, square roots, right? In Daniel's book, they call them surds. Like the square root of 2 and the square root of 3 are surds. I don't know if we really have that. I think we tend to just call them radicals. But anyway. Okay, so. Excuse me. Let's see here. So he says, recall every finite group is isomorphic to a subgroup of some symmetric group Sn, right? And it's an open problem to determine whether every finite group appears to be a Galois group for some polynomial over Q. I mentioned that in the lost lecture. But if you look at sections 14.4 and 14.5, a partial answer is already given to that question. There are many. So, for example, one of the things we learned in 14.5, I think, on the cyclotomic things is that the, or was it the, yar. Yeah, so in 14.5, the cyclotomic extensions, we learned that the Galois group of Q adjoin zeta n, right, is isomorphic to the multiplicative group Z mod NZ. So like, I'll write it down. So so the Galois group of Q adjoin zeta n over Q, right, was isomorphic to what Galilean's abstract algebra calls UN, but Dummett and Foote calls Z mod NZ X. That's their notation for the group of units in Z mod NZ. So already there you see that you can, any of the group of units of Z mod N is a Galois group, right? For what polynomial? Remember that the other thing we talked about was that this is the Galois group of the cyclotomic polynomial, right? So this is the splitting field for phi n of x. And the degree of this is exactly the Euler phi function. It's phi of n, right? The order of this is phi n, which is obvious from this. But anyway, like he was saying here, it's an interesting question whether every finite group is the Galois group of some polynomial. So that's an open question, at least at the time this was written, and as far as I know, it's an open question. All right. So going forward, we shall explicitly determine the Galois groups for polynomials of small degree, in fact, up to an equal 4, below which we will show that, in particular, every subgroup of S4 arises as a Galois group. So, all right. And so in order to do that, we have to build this machine of what are called elementary functions. So let me get into that. Let's see here. Do, 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 do. What's that? A moment of silence for those who took this physics test today. That's usually a good bet. Yeah. Physics is hard. All right. So definition. So how to explain what we're doing. We're trying to. I don't know how to explain it. You just have to do it, and then once we've done it, it'll start to explain itself after a bit. But there's something very, very conniving what we're doing at the moment. Okay, well, it's simple, and yet it's bizarre. Well, I mean, like Lagrange multipliers in Calculus 3. Like once you learn Lagrange multipliers, it's pretty simple. But at the start of it all, it's like, what? Why? You know? Or Laplace transforms in differential equations.
Oh, yeah.
Why are we taking the integral from 0 to infinity of e to the minus st times the function? Why would you do that? But then you do it, and you see what magic it does, and you're like, we should do this. This is a good thing to do. But at the start of it, like, what motivates that? There is a video made by MIT professor who's taught, differential equations to, MIT, the best of the best engineers for decades and decades, right? Mm-hmm. And he does have about a 20 or 30 minute on-ramp to explain where that formula comes from the perspective of signal processing. In terms of something called the discrete transform. It is the continuous, it's like the continuous version of something they're more familiar with from a discrete side of things. But unless you really, really knew about that discrete thing, it's still kind of like explaining something you don't know with something else you don't know, like you just said. So, yeah, the Laplace transforms is a sticky wicket. Let's see here. So, definition. Let x1, x2, xn be indeterminates. The elementary symmetric functions S1, S2, Sn are defined by, here we go, S1, is S1 plus S2 plus Sn. S2 is x1. Oh, I'm an idiot. X1 plus X2 plus Xn. That makes more sense. Okay. S2 is X1, X2 plus X1, X3 plus X2, X3 plus X2, X4 plus Xn minus 1 Xn. So I could express that more sort of concisely here. This is the sum over I not equal to j, right, of x, I, xj. How many terms are there? No.
Is it when you get n that way and n that way?
We're taking n things,
Yeah, and multiplying it.
and we're picking, from those n things, we're picking two indices
Yeah.
without repeating. This is n choose 2. Which is what? N factorial over 2 factorial times n minus 2 factorial, also known as n times n minus 1 divided by 2. So for example, it's the binomial coefficient. So when n equals to 5, for example, there are 10 of these things added there, which if you want me to rattle them off, like 1, 2, 1, 3, 1, 4, 1, 5, 2, 3, 2, 4, 2, 5, 3, 4, 3, 5, 4, 5. Yeah, I don't think Gauss knew this when he was 6. But let's see here. Gauss did there's something similar that Gauss did, the sum of the first numbers from 1 to n. Now Sn is just x1, x2, x, xn. So what's the deal with these guys? What's the structure we're looking at here? So these formulas, the formulas for S1, S2, all the way out through Sn are invariant under any permutation of the indeterminates. Right? See, if I permute the indeterminates, I still have the same formula, right? Because these are commuting. We assume indeterminates are commuting indeterminates, yeah? So like, for example, if I did the sigma, which was, the n minus 1, 3, 2, 1 permutation, right? Then if I do that permutation to these indices, what do I get? I get I get Sn maps to, x what? 1 maps to n, 2 maps to 1, 3 maps to 2, and then n maps to n minus 1, right? But of course, that's just equal to Sn again, right? So all of these formulas are invariant under a permutation
Yeah.
of the indeterminates. Okay? Now, definition. So, I'll put it here. I may regret it. Definition. The general polynomial of degree n is x minus x1, x minus x2, dot, 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 x minus xn with roots the indeterminates. It's so simple, it seems like it can't be helpful. But no, it is, yeah. It doesn't seem that simple. Oh, so.
Simple things help the most sometimes.
Now here is an interesting claim. It's easy to see by induction that the coefficients of the general polynomial of degree n are given by the elementary symmetric functions of the roots. Here's the claim. X minus x1, x minus x2, x minus xn is equal to x to the n. Well, that's easy enough. Minus s1, x to the n minus 1, plus s2, x to the n minus 2, plus minus 1 to the n, Sn. Now, of course, you could go through the induction. I've done it before. It's not that exciting. I think it's more fun to just try to just kind of multiply it out, which is not a proof, but I think it's maybe more instructive to just do it for, like n equals to 3, for example. So you have x minus x1, x minus x2, x minus x3. So you have x minus x1, x squared, minus x2x minus x3x, plus x2, x3, which then is x cubed minus x2, x squared, minus x3, x squared, plus x2, x3, x, minus x1, x squared, plus x1, x2, x, curses, plus x1, x3x minus x1, x2, x3, which is equal to x cubed minus, well, the x terms. I've got a x1, excuse me, x squared terms. I got one here, I've got one here, so x1 plus x2 plus x3 times x squared, right? And then how about the x terms? Plus, I've got x1, x2, x1, x3, x2, x3, x, and then minus x1, x2, x3. I think I'll zoom in on that a bit. I need to get a, I think my lens is a little bit dusty. So what are we looking at there then? You can recognize what you got, right?
Yep.
That's
S1.
exactly, this is the S1. This is S2, and this is S3. So indeed we have x cubed minus S1 x squared plus S2x minus, well, rather plus minus 1 to the third power, S3, right? So there you go. That's how this claim works out in n equals to 3. And again, you can prove this inductively holds for n. Yeah. Now, what's interesting is this, right? Here's what's interesting. Let's see here. He says for any field f, right? Let me write it out. For any field f, all right? The, lost my place again, curses. Where'd you go? Ay, ay, ay. The extension f of x1, x2 dot xn, right, is a Galois extension of f of S1, S2, Sn. Since it's the splitting field of the general polynomial of degree n. Let me call this thing k, since k splits, you know, f of x, x minus x1, let me zoom back out before I regret my life. Let's see here. Ah! Had to learn to do my own camera work since I've started working here, you know. Here we go. that make sense? I'm trying to process it. Like when I first wrote it down, I really want it to be the extension to go the other way. For reasons for fuzzy intuitive reasons I can't explain. So let's see here. Let's put it this way.
Okay.
It splits like this,
Yeah,
but
the claim, yeah.
it splits this f of x. But the f of x we're splitting, it actually splits, the x to the n minus s1
Yeah.
x to the n minus 1 minus 1 to the n Sn, right? This is an element of f s of s1 Sn. Right? Yeah, I mean this. I don't need the field here. It's it's a polynomial, right?
Yeah.
Well, I mean, I don't know, notation is failing me, but this is a polynomial with coefficients in the symmetric functions, right? That is clear. And it's also clear that if we believe the induction claim, that polynomial that I just wrote and underlined in orange, this expression right here, splits into like this right here, right? And where is this happening? This is happening in K, right? In the field extended by all the indeterminates, x1 through xn. Now, the claim is that the claim is that f of x1 through xn is an extension of the symmetric functions. Does that make sense? Like just in terms of set theory? Do you see that? So if I call this thing K and I call this thing L to go against Conrad's notation, unfortunately, is it clear that K is an extension of L?
I think so.
Right.
Because every S, like S1 is are we considering S1 a polynomial?
Are you considering S1 has a definition? It's over here for a fixed n.
It's not a polynomial, it's roots, right? Combined indeterminate roots.
Yeah. Let's hear. Yeah. Mm-hmm.
So yeah, that makes sense because if we have a splitting field or I guess it's not a splitting field, but let's say L is a splitting field of indeterminates like lower than that. F holds all those polynomials, or not polynomials, all those roots that S holds.
Mm-hmm.
And so if that's the case, if K would have to split everything in that.
Right.
Yeah.
I'm a little bit concerned that they're the same thing, but I guess that's not true. Like here's an example. This is n equals 2. Here's my K, here's my L. This is the n equals 2 case, right? So clearly L is a subset of K, right?
Yeah.
L is a subset of K because if you have the field containing x1 and x2, x1 plus x2, right? I mean, obviously x1 plus x2 and x1, x2 are elements of K. Hence, L is a subset of K, right? And that's generically true at order n. Like I'm showing you n equals 2, but if you think about it for order n, it's no different. Definitely, we can build all the symmetric functions from what? Sums of products of the indeterminates. Those are field operations. So it makes sense to say that that's an extension.
Yeah.
The only thing I'm slightly worried about is like, are they equal? But
Yeah, but
I mean, that wouldn't be bad.
I